Okay, and I think we can start. We are now live on YouTube.
Okay.
So first of all, welcome to everybody watching us right now, and to everyone that watches later. I also want to start by welcoming our speaker for this session of IAPS at a Distance about gravitational wave cosmology, Dr. Misao Sasaki. I will read a short biography of Dr. Sasaki before giving him the word for his presentation. So Dr. Misao Sasaki received the degree of Doctor of Science from Kyoto University, Japan in 1981. Having general relativity and cosmology as research fields, Dr. Sasaki has worked at various universities. He was director of the Yukawa Institute for Theoretical Physics of the Kyoto University from 2013 to 2017, professor emeritus of Kyoto University since 2018, and has been since 2018 a deputy director of the Kavli Institute for the Physics and Mathematics of the Universe of the University of Tokyo. In 2008, Dr. Sasaki received the Humboldt Research Award. And now I welcome you, Dr. Sasaki. Thank you for accepting the invitation for this talk.
Thank you, Duarte.
I now give you...
well, yes, so shall I start?
Yes,
is that okay?
Yes.
Yes, so today I'm going to talk about this gravitational wave cosmology, which is a very, very new area of research, but which is booming. Now, lots of papers are published recently, and it's rising rapidly. So it's really an exciting field. So let me explain. But before we go into this, the actual topic of the physics, let me first introduce this, this organization, which is called the AAPS, which is an Association of Asia Pacific Physical Societies. And especially, there's a division called Division of Astrophysics, Cosmology, and Gravity, DACG. And so this is where we sort of promote the science in the Asia Pacific region. But of course, this society is open to, in terms of events are open to everybody from all over the world. And we try to sort of, have lots of interactions. And especially these days, we plan. Hopefully, we are talking to people from European physical societies, and hopefully we will have some kind of a memorandum of understanding, and have joint events and so on in the future. And especially about this DACG, we are having some organizing or sponsoring some international conferences, and these are some pictures from this AP stands for Asia Pacific, a school and workshop on astrophysics, cosmology, and gravitation. And at this AP school, we have a few lectures by some world prominent experts in various fields. And so as you see, there are lots of students attend, and graduate students in this case. And also we have some presentations by those students, which is done in the workshop. And so we are doing this every year, and in order to promote science in our area. Okay, so that's the introduction of this Division of Astrophysics, Cosmology, and Gravitation in AAPS. Now, let me go back to physics, gravitational waves. Okay, so what are gravitational waves? Gravitational waves are ripples of space-time, so-called. It's the fluctuations of space-time itself, propagating at the speed of light. And the first predicted by Einstein in already more than 100 years ago, 1916. But as we will see, it took more than 100 years to actually discover it. Anyway, so the theory, this theory of Einstein's theory of general relativity, predict that when some mass or energy distribution is rapidly or violently fluctuating, then that will cause fluctuation of space-time, and which will propagate and emit it. So and the gravitational wave propagates by stretching and contracting in the space perpendicular to the direction of propagation. So this is, as I show you here in this picture, so it's a kind of a quadrupolar deformations, and so for example, you have a round ball with the squeeze into this elliptical figure, and then to the prolate, oblate in this way. So this is called the quadrupole wave. And here's the equation, which is the only sort of mathematical equation I wrote in this during this talk. So those students who have already studied some differential equations may be able to solve these equations, by the way, and find some wave propagating, gravitational wave propagating in the space-time. So this is in contrast to so-called electromagnetic wave, which is it also it deforms the electromagnetic sort of a field in a perpendicular way, but it has the property of a dipole nature. Dipole means that if you rotate around 360 degrees, it come back. Yes, which is also called spin one. And in the quadrupole case, as you can see, that if you go around 360 degrees, you repeat the same pattern twice, and this twice means that they have spin two. Anyway, so those are the waves, but the whole point different. What's the most different thing from the gravitational wave from the electromagnetic waves is that they are its interaction is very, very, very weak. They merely do not interact with anything. And therefore, for example, in the case of electromagnetic wave, we know our universe was very hot and dense in the very early universe, where the light cannot sort of propagate directly, but be scattered by various particles, especially like electrons. And so until the universe becomes neutral by when those electrons are captured by protons and the universe becomes neutral, the electromagnetic wave cannot propagate directly to us. So this means that if we use the electromagnetic waves to observe our universe, the deepest universe you can go to is here. It's a small number. It's about 380,000 years from the beginning of the universe. That's the limit, and you cannot go beyond because of the scattering. But the gravitational wave do not scatter, and so you can just go very, very deep into the very early universe, and there's a chance we will see the very interesting, probably exciting events happening in a very, very early universe. So this is one of the new tool we obtained very recently. Now, so where do gravitational waves come from, apart from those from a very, very distant universe or early universe, which I will come back later. So one, which is most important, is called gravitational wave from so-called binary neutron stars or binary black holes, or in general, binary compact stars. So you have some two compact stars, either neutron stars or black hole. So they form some binary system, but because of this motion, they emit gravitational wave like this left figure, and emitting gravitational wave, they lose the energy. And when you lose the energy, the gravitational system become more tightly and tightly bound. That's the interesting point of gravity, anyway. And so and in the end, it coalesces. So if you watch this sort of a binary so-called in spiral, we call it, by gravitational wave, then in the beginning you have some fairly periodic waves, but gradually this period becomes shorter and shorter, and the amplitude becomes larger and larger, and in the end it boom, they collide each other and form something some with a large mass thing. And if these two are neutron stars, then we think that the collision merger of these neutron stars would form black hole. If those two are black hole, of course, eventually you have two black holes merge into one black hole, one big black hole. But anyway, the whole point is that by observing those emitted gravitational waves, we sort of probe properties of very strongly curved space-time or matter under extreme conditions. So this is a new tool to understand not only astrophysics things, but very interesting physics, fundamental physics. Okay. Now, so about already 5 years ago, just about 5 years ago, this LIGO, which I will explain, is some detector system detected gravitational wave from binary black holes for the first time, and this happened in September 14th, 2015, which is almost exactly about 100 years after the discovery of general relativity by Einstein. And they are very lucky. This was only 2 days after the machine started to operate. And they found that actually the black hole had surprising large mass, 30 solar mass. Solar mass, it means that it's the mass of the sun. Sun is really, really heavy. But the black hole, it's about 10 million times bigger than yeah, more than million times bigger than the mass of heavier than the mass of Earth. But this 30 solar mass means it's 30 times more. And those huge and heavy black holes happen to collide, and they are at the distance of about 1 gigalight year, which is a very, very far away. But in terms of the cosmological distance, it's not too far away. And because of that, it was in some sense close enough, and so that they could detect this. And the important thing, or in some sense, is that so if you have 30 solar mass black hole, two black holes colliding, you would form a say 60 solar mass black hole. But because of this very, very violent sort of oscillations of the space-time and so on, the part of the energy is actually emitted as gravitational waves. And this energy is almost like 3 solar mass. And this energy is huge. If you, for example, compare the supernova event, supernova is, happens every maybe once in 100 years, so in galaxy. And when it happens, the brightness is as bright as the brightness of the galaxy itself. Now, this in terms of energy, the gravitational wave emitted in this event is about 10,000 times one supernova. So it's in terms of energy, it's a huge, most energetic event in the world, in the universe. Now, so what is LIGO? LIGO stands for Laser Interferometric Gravitational Wave Observatory. And there are 2 detectors, one in the Hanford, Washington, and the other in the Livingston, Louisiana, in the United States, and they are separated by 3,000 kilometers. And I will come back to this number, but there's 3,000 kilometers means that if you travel by light speed, it takes about 10 milliseconds. Now, so you have this rectangular kind of L-shaped arm, and this arm with about 4 kilometers length, and it can detect the gravitational wave amplitude of about 10 to minus 21, which means that the fluctuation in this distance would be about 10 to minus 16 centimeter, which is like 100, well, 1,000, a few hundred times smaller than the size of a nucleon, one small nucleon, proton, for example. So it really can detect very, very tiny fluctuations. And here's the sort of the principle of this interferometer detector. You have this L-shaped arm. Oh, here, yes. Yeah, sorry. So this is L shape. And you have a laser input. And then when the gravitational wave passing through, then as I said, you have some quadrupole sort of deformation of space. So it's not really, there was the kind of mirrors which reflect the laser light is moving. It is just staying static, but it's a space in between which is shrinking and decreasing in length. Now, because of this, then you have the interferometric sort of pattern in this detector, and by measuring this bright and or the dark sort of spots and so on, then you can detect how big the amplitude of the gravitational wave is and how frequency and so on and so forth. Okay, so this is the LIGO interferometer, and so the size of this is the this arm length is about 4 kilometers. Now, what they have observed is this. So the upper panel, the actual wave patterns they observed, this oscillations pattern, and the left one is the Hanford, Washington, and the right one is Livingston, Louisiana, and actually the blue one is Livingston, Louisiana, and the light sort of orange one in behind is the Hanford. This left one, which is sort of fitted to this curve, and they found that there's some time difference of 7 milliseconds. Now, as I told you before, one step before here, that the distance between these two detectors are 3,000 kilometers, and if you travel by light, it takes about 10 milliseconds. When, for example, when the wave comes from this direction, then wavefront would reach these two detectors at the same time. Therefore, there would be no time differences. But if the wave comes from, from this direction, then after you measure this gravitational wave, it takes about 10 milliseconds to arrive this. So you will have a 10 millisecond time difference. In any case, if you are measuring the gravitational wave, the same gravitational wave, not other noise or anything else, then this time difference must be within 10 milliseconds. And the fact that it was 7 milliseconds is almost sort of parallel to this, but slightly off in this direction. So this means at the same time, this time difference can tell you approximately from which direction the wave came from. Anyway, so so by this, and the lower panel is the numerically simulated waveforms, and which they actually, after the discovery of these waveforms by LIGO, and as you could see, it fits very, very well. So this sort of it means that they did really discover gravitational wave from those binary spirals. Okay, so since then they have already actually discovered 10 binary black hole events, and after that a short sort of interval, they start operating sort of upgraded version of LIGO with this Virgo machine, which is the actually machine in Europe, Pisa, Italy. So with 3 detectors, they started to operate so-called observation 3 experiments, and about 1 year, sorry, from April 2019 to March 2020. Unfortunately, because of this pandemic thing, that they should stop, they had to stop the operating around the middle of March. Anyway, so during this 1 year run observation, they already discovered about more than 37 binary black hole candidates. So altogether, there are already like 50 binary black hole events candidates. And now you are starting to do some astrophysics astronomy out of these numbers. And they are now stopping, and then they will upgrade the machine, and within a couple of years they start operating again with further better sensitivity. Now, since I'm from Japan, let me just talk a bit about Japan. We have a similar machine. It's the arm length is about 3 kilometers. instead of 4 kilometers, so it's a bit small, but it's underground in order to avoid any sort of earth fluctuations or noises, which is called seismic noise. And it is called KAGRA. KAGRA stands for Kamioka Gravitational Wave Detector. Kamioka is the place where the so-called neutrino detector is. And so this super Kamioka detector also is playing a very important role in astrophysics and cosmology. But today I'm not touching that topic. So anyway, so this Kagra actually in Japanese can be written in this form. This Kagra. Well, this first character means God, and second character means music. So actually, this Kagra can mean that God music in Japanese. Anyway, so whole point is, so this is, if this is in operation and becomes as sensitive as LIGO and Virgo, then they can join this international network of operations. Now, of course, at the moment, as I say, it's only 1 megasub. The sensitivity reaches only to 1 megaparsec, which is about a few hundred times smaller than, shorter than the LIGO Virgo. So we do need to improve the sensitivity a lot by a factor of about 100. But if you look at this sort of increase in the sensitivity, due to really a very lots of effort by those people working in Kagra, so they have it's a factor of 10 improvement in about 2-3 months. So maybe factor of 10, 100 improvement can be done within a half year or 1 year or so. So this means that within a couple of years, when the LIGO is upgraded, maybe they can join to this LIGO Virgo collaboration operation observations, and then they can play a very important role. So in any case, so in future, by the way, so there's another one which is the will be constructed, is the LIGO India. This is the same machine as LIGO machine, but it will be placed in India. And well, we don't really know when it will be constructed and finished. But anyway, so hopefully it will be done within 10 years or so. So right now we have 2 LIGO detectors and the Virgo joined. So we have three detectors working. If Kagra, or this is 2020, maybe 22. If Kagra joins, then we will have 4. And if LIGO India joins, then finally we will have 5 sort of a large-scale gravitational wave detectors on the Earth. And these 5 machines will be a very important, network will be very important, which I will explain right now. So the whole point is that angular resolution. When you look into the sky, for example, with some telescope or anything, then the most important, well, maybe one of the, you could say, but I would say the most important sort of a point about the good telescope is the angular resolution, how good the telescope angular resolution is. Now, this S over N, this is called signal to noise ratio. So for example, if this is signal to noise ratio of 18, means that the signal is stronger than by a factor of 18 from the noise. So this means that you have some fairly large signal, which you can say see, maybe not by eye, but by analyzing the data. Now, so this GW150914, this was the first event. In this case, there are only 2 LIGO machine, but because the mass of black hole was so huge, you had a signal to noise ratio about 24. Now, about 1 year later, when the Virgo joined and they had 3 detectors, this black hole, it was a bit far away, as well as the mass was a little bit small, and the signal to noise ratio was slightly down from this 24 to 18. But if this is angular resolution from this 2 LIGO. although the signal is so strong that it's definitely, you can definitely tell you that it's the gravitational waves, but since it's only by two detectors, it's very difficult to identify the direction from which those gravitational waves came from. But when Virgo joined, the three detector made this huge sort of a bad angular resolution into very, very small region. So in some sense, signal to noise ratio is also, of course, very important. But to do some a meaningful astrophysics astronomy, then you need a good angular resolution. Now, so this just adding one machine made this angular resolution very good. So we will have this Kagra and LIGO India eventually, and then eventually, at least as far as the planned detectors are concerned, we will have 5 detectors, say within at least 10 years or so, running, and then these 5 detectors actually can be used to actually make angular resolution very, 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 very good. So in that sense, actually, of course, each detectors are important. Each detector is important, but and they can each can do some interesting sort of detections and interesting physics, cosmology, astrophysics, and everything. But this joint observation, this network observation, is really the key to the future. So you cannot do the new physics without this collaboration, network collaboration. This is a very additional new sort of a type of international collaborations. So that's another thing. This the gravitational wave astronomy cosmology is bringing us. Oops. Now, what's next? Okay, so after binary black holes, actually, again, about a couple of years after the first discovery of binary black holes, the Virgo LIGO team found a coalescence of the binary of the merging of binary neutron stars, and so and fortunately they're very close enough. Remember that the first LIGO event was about 1 giga per second. Oh, so maybe this is 200. No, yes, it's one giga, and this is, oh, must be. Oh, sorry. This must be 120, huh? Mega light year. But anyway, so maybe I should sorry. Yeah, but anyway, it's a closer, much closer. This is the reason why that they could see it. And the important point is, in this case, you have matter and you have very sort of a high density matter colliding, and therefore you expect a huge electromagnetic events occurring. And actually, it was the case. Actually, at almost exactly at the same time, this a Fermi a satellite, which is the satellite which is to find some gamma ray burst in the universe, detected this gamma ray burst from essentially the same direction, and which is called 1708. 17A, the level A is for it was the first event on the day. Nowadays, the gamma ray burst is found a few gamma ray burst is found a day. So so they have A, B, C, and so on and so forth. But anyway, so it's very important that they are now not only you have observed this merging event by gravitational waves, but you have seen by electromagnetic wave as well. And so this is very, very important. And they actually, and another important thing, that's this is the gravitational wave signal in some way to show the this is frequency, amplitude and frequency. Frequency is going up and amplitude going up, and this is the coalescing merging event time. Now gamma ray signal had a peak from about 1.7 seconds after the coalescence of a binary neutron star. So this actually means that you can interpret this for from various point of view. But one, oh, by the way, maybe I should, before I should go into that, it's 1.7 second thing. Let me show you that. So since then, that all people all over the world, all the many astrophysics observational groups started to observe these events. And actually, it was observed in X-ray and UV, optical, IR, and radio. So all this is almost all frequency band of electromagnetic waves. And then they have seen, and because of that, you can clearly identify the position of these events, and so gravitational wave. Yeah, as I said, because of these three detectors, the angular resolution becomes very good, but still the angular resolution of the gravitational wave detectors are not as good as those by, for example, the radio telescope. And if you use the radio telescope, you can really see a very actually pinpoint the source astronomical body. And because of this, you can clearly identify the source and do the various physics or astrophysics from the data. Now, so this is what we call the dawn of multi-messenger astronomy. Multi-messenger means from various, of course, not only various frequency, but various different tools like gravitational waves and electromagnetic waves. Now, in future, probably we will add to this the neutrino observations, and it will be really multi-messenger astronomy, and this will deepen our understanding of the universe definitely. And as you could see that in this case as well, although now it's slightly different from this LIGO-Virgo kind of international network, but still, having all these other sort of observatories all over the world, and you observe the same thing, and you analyze the data, which can bring us much more richer sort of understanding of our universe. Now, let me go to the most important thing, to the cosmology. So one of the most important implications of this binary neutron star merger, GW170817, is that actually you can do cosmology because now you see what the electromagnetic light, and which means that you can identify the source galaxy, and if you see the source galaxy, you know how rapidly this galaxy is receding, and which is called the Hubble-Lemaitre's law, that the famous law that which tells you our universe is expanding. So if the galaxy is far away, then the velocity, which corresponds to the receding velocity from us, is becoming larger and larger. And of course, this receding velocity cannot be seen by measured by itself, but actually you measure the redshift. If it is receding, it's like this, the sound, which when the car is going away, the sound of horn will go lower, while when it approaching, it becomes high pitch. So this the same thing happens to the light, and you observe the redshift, and from redshift you sort of infer this recession velocity, and if you know the distance to that galaxy, you understand, you know what this coefficient is, and which is called the Hubble constant. Now, without the gravitational waves up to now, of course, so the left-hand side, velocity or the redshift can be measured, and of course there are all these intrinsic motions and all these things. So there are some systematic errors, but still this can be measured. That's important. But the distance to the galaxy can only be estimated. You have no means to measure the distance to a certain galaxy, a distant galaxy. However, gravitational wave actually can provide that tool, because since we know how those binary sort of coalescence proceeds, and you have a very accurate theoretical templates, actually you can by looking at the waveforms, the amplitude, frequency, and so on, and then you can sort of actually measure the distance to that the event. So now, of course, it will have some systemic errors as well. So that's why it's not a single point. But in any case, now we are in the stage where the left-hand side of this Hubble metals law can be measured, and also the right-hand side. And therefore, both can be measured. And this will sort of, in some sense, revolutionize our sort of understanding of the universe, because we have completely independent, in some sense, from the this point of view of the measurement, a direct measurement of the Hubble constant, and then for which we measure the distance by gravitational waves, we measure the redshift by electromagnetic waves. So this multi-messenger sort of concept is really the heart of this measurement, and the determination of Hubble constant. So this will probably change the view of cosmology, as when we have more and more data on the of binary neutron coalescence. Okay, so another thing is that the another implications is that the about the propagation speed of electromagnetic waves and the gravitational waves. Now, as I told you that there was about 1.7 second delay of electromagnetic or gamma ray arriving at on the Earth. So, and we know the distance, and if you know the distance, if you know that the time difference, if you even if you okay, if you assume that they emitted at exactly the same time, you see that the velocity of propagation velocity must be very the difference in propagation velocity is very small. And in fact, it's very easy to compute from this number that this difference of the propagation speed is about 10 to minus 5 centimeter per second. So this means essentially there are no difference. So this kind of thing actually constrain the theory of gravity, which now people talk about a lot, especially to explain so-called dark energy, which drives the acceleration of our universe. These models can be strongly constrained by this data. So just one single event of this neutron star coalescence had a very strong impact on cosmology, one in a Hubble constant, the other on the dark energy models. Now, so how about future? So we have the future space observatories planned, and some, a few of them. That is one called the SIGO, which is about arm lengths of 1,000 kilometers, and they can detect the gravitational wave frequency of about 0.1 hertz. And in the Europe and US now has this LISA. This is the Laser Interferometer Space Antenna project, which will hopefully launch, and we're going to see the result within 15 years or so. The arm lengths of this is an artistic view of the LISA. You have three sort of satellites, and each arm length is about 5 million kilometers, and they will detect the gravitational of the frequency of 10 to minus 3 hertz. Now, recently China started to make some proposals for the large-scale sort of these space interferometer detectors. They have two proposals, and we don't know whether both of them will be approved or maybe only one. But anyway, the one is called Taiji, the other called Tianjin. And they also expect to be launched around the same time as the LISA, and they have about approximately the same frequency band. In any case, so we are expanding not only in the it's not only, sorry, expand in the frequency range. Oh, by the way, maybe I should have told you for the frequency. the gravitational wave frequency here is about as you can see, it's about 10 hertz or so. In the end, it's like 100 hertz. So 10 hertz to 100 hertz. So this, you know, by having those interferometers in space, will expand the frequency band of the gravitational wave observations. Now, even for very, very low frequency of about 10 to minus 8 hertz, which means that the one oscillation, it takes about 10 years, period of 10 years. For those such a huge, long wavelength gravitational wave, actually, pulsars can be used as detectors. So when the pulsar is known to be a very, very accurate clock. So if a gravitational wave passing through between the pulsar and the Earth, then because the distance between pulsar and Earth will be slightly changed, and the slight change will cause time advance or time delay in this timing period of the pulsar. And if you just observe one pulsar, then of course you don't. It's very difficult to extract out that such effect. But if you have hundreds of pulsars, then and by statistically you can measure the how much gravitational waves are propagating in the interstellar space. So this is called pulsar timing array, and so this is another very, very promising sort of a way to measure gravitational wave in the universe. And altogether, you have this so-called multiband gravitational wave astronomy, astrophysics, or maybe you could call cosmology, that they are from the about period of 10 years or maybe even up to 100 years down to 1 millisecond. And this 1 microsecond is the future thing, which hopefully, if somebody has some really brilliant idea, then well, at least the size of this detector can be just on tabletop size, and on tabletop size, maybe you can do a very, very interesting gravitational wave experiment. So anyway, so this multiband gravitational wave astronomy is started to bloom. All right, now let me just using the last 10 minutes or so, the gravitational cosmology, a couple of talks from gravitational cosmology. So one is the gravitational waves of inflation. As many of you may know, that in the early universe, it is believed that our universe had the stage of so-called inflationary expansion, where the universe expanded exponentially, and because of this exponential expansion, when any space has some so-called vacuum fluctuations, if you quantize the field, the matter field, and everything, even the space-time, you have small fluctuations. Those vacuum remains in vacuum in the standard ordinary space-time. But when the universe expands exponentially fast, then those vacuum fluctuations wavelengths are also stretched exponentially, and they will end up with some frozen static kind of a pattern in the universe. This static pattern in the universe, if it happens in the energy density of the universe, it causes all these it is a seeds for those structures like galaxies, stars, and all the things, and eventually us, our human beings, and all the creatures in the universe. So anyway, so this is what happens, and which is of course which such an effect, of course, is true for so-called this pure quantum space-time fluctuation. Actually, these pure quantum space-time fluctuations are gravitons, we call, and when it stretches and then they becomes kind of a very, very long wavelength wave, we just call them gravitational waves. Now, so this gravitational wave can be measured by some small pattern in the so-called cosmic microwave background, which because of some small fluctuation in space-time can be imprint in those effect in the propagation of the the electromagnetic waves. But if you just see the temperature fluctuation of those electromagnetic waves. The effect of gravitational wave is too small to be measured, but fortunately, there is so-called Dmode polarization. Electromagnetic wave has two mode of polarizations, and you can decompose them into so-called A mode and B mode. Essentially, it's the even parity and odd parity modes. So you have the when you do the parity transformation, E mode remains the same, while the B mode change the sign. Now, this B mode can be produced. I don't know. Sorry, all these density fluctuations I just mentioned, which causes those temperature fluctuations in the cosmic microwave background, can produce only E mode. So if you can find any primordial B modes in this CMB sky, then that's a proof that there was a gravitational wave in the very early universe. In some sense, measuring this B mode polarized light with a certain period of about this 10 maybe too much, maybe 1 giga years, means that you have the gravitational wave detector with arm length of 1 giga light year. So now you expand this frequency band to extremely large widths. Now, and another thing, of course, you may have is that the gravitational wave from some phase transition in the early universe, for example, what we call the electroweak transition, where this famous Higgs field gives rise to the mass of matter, and this transition, if it has so-called first order, strongly first order, can form some interesting bubbles and so on, and then the collision of the bubbles may produce gravitational waves, which may be detected in future detectors. Okay, so another thing is that of course, in the early universe, maybe you may produce some primordial so-called primordial black holes, which are not black holes produced in the recent days by this gravitational collapse of stars, but which appears in the very, very early universe. And if those black holes are produced at when the universe temperature is like 10 to 12 Kelvin, or about 100 MeV, then those black holes actually can explain LIGO binary black holes. So now we have to differentiate whether there's a LIGO binary black holes or primordial. And again, if you in the future, we will have a detector which can detect very, very the gravitational wave from very early universe, not too early universe, but the universe after when the universe was 10 million year old or so. So if those binaries are primordial, you will still see the events, those are coalescing events in the early time, in the early universe. While if those binary black holes are the astrophysical black holes, which are produced from produced from some collapse of stars, then the number of those black hole coalescence events will decrease eventually if you look back early in the universe. Therefore, you can definitely test these models by gravitational wave detector. So in all that, we have a really a era of the gravitational wave cosmology. And as I have told you that at least we are now already coming into the stage of multiband gravitational wave astronomy. Multiband means the frequency band, which ranges about maybe 5 orders magnitude or so, but or 10, even 10. But if you go to the CMBB mode observations from the very early universe, from inflation and all the other things, then altogether we will have a gravitational wave, a multi-band cosmology from a period of 1 giga-year to 1 millisecond, which is about 20 digits. So this is really a interesting, interesting future, and cosmology will undergo a revolutionary change, I'm sure. So coming back to this figure again, the gravitational wave penetrate everything. Therefore, that's one of the reasons why it's so difficult to measure. But if now we have a very accurate sort of detectors, and also we have very good detector plans, and within 10 or 20 years, so that we start to really probe not only the all these black hole events, neutron star binary coalescence events, and so on and so forth, but some all these interesting events from very early universe and beginning of the universe may be probed. And in the end, this is the conclusion that the gravitational waves are an indispensable tool to explore the unknown universe and discover new physics. And we never know what will be discovered next. Stay tuned. Thank you very much. Okay. Oops. So
okay.
Yeah.
Can you hear me?
Yeah, I do.
Okay. Thank you very much, Dr. Sasaki. This was an incredibly interesting presentation. And I actually think you covered a lot of questions that I was going to ask you already. But now I think we can still have a few questions for you.
Right.
So I first would maybe ask you sort of a two-sided question, which is, first of all, how did you get into working in gravitational physics and gravitational waves in particular? And what are you, what projects and research are you currently working on yourself?
So yeah, well, as for the first part, well, I had interest when I was still very young, interest in general relativity, because probably it's very similar to many of the young people that you're fascinated by this general relativity, because they theory tells you that this space time is not just space time, but it's dynamical and so on and so forth. It's really exciting, huh? So that's definitely the reason. And then when I started to study this relativity, of course, the gravitational waves, one of the, in some sense, simplest subject, and it has rich a sort of a topics, but it's simplest because you deal with small fluctuations. Small fluctuations are always very easy to deal with. So that's one of the reasons why I get into this. So right now, actually, which is it's I can this well actually maybe I should go first. Yes. So this scenario, as I just briefly talked about, this maybe those black holes we measure today, binary black holes, may be primordial. And this is one of the topics I'm very much interested in, and I've been working on this late in these years. So there are several others, but this is one of the main sort of subject I'm working on. So did I answer your questions?
Yes, I think you did. Thank you very much. And I think it would be interesting also if you could sort of give any student that watches this an idea of what they should, of course, in a lot of physics courses, especially in masters, there's already study of general relativity and cosmology. But if you could sort of point in the direction of what students, so what sources, let's say, should they follow in terms of research to get an idea also of the current updates that there are.
Yeah. So these days actually you find so-called the archive. There's this you call so preprint archives, huh? Which is called ARXIV archive .org. And if you go there and you can find some updated sort of new papers, actually too many papers perhaps. So then there's also a site which is called the Inspire, which is operated by I forgot which Cornell University, maybe was it? But anyway, so and in terms when yes, there you can find many sort of also the all sorts of references and papers and so on and so forth. And the good point is that they give you the how many citations each paper got. So if you just look into some of the papers which you search for the titles of your interest, some keywords and so on, and then you just find some maybe well-cited papers, which must be something very interesting. So maybe you can start from that. Of course, and if you have some senior colleagues, senior teachers around you, then the first thing is you should ask them, right? Is that okay? Oops, you're frozen again.
Yeah, thank you very much. I would also like to mention regarding the you mentioned that you have measures of the B modes, and there's sort of a picture of a satellite or
oh yeah. Oh yeah. So yes. So actually, this is called Lightbird. Yeah, which will be now. Just last year, this project was approved by.
Maybe if you could talk a bit more, if you know.
Sorry, I cannot hear you. Maybe some problem with your connection again.
Okay, can you hear me now, Dr. Sasaki?
Yeah. Yes. So maybe I lost your question. I don't know. You talked about this satellite, or
yeah, I think I lost a bit of your answer. So if you could just talk a bit about the Lightbird.
Yeah. So this is a satellite project, which is international, but essentially based in Japan. This JAXA, this is the Japanese, I don't know, aeronautical, whatever, this agency which launched the rocket, is the central sort of this project. But anyway, this Lightbird is international collaboration project, and this about, well, it costs a lot. So this JAXA they had to approve this. There was some meetings and so on. And just last year, 1 year ago, this was finally approved by JAXA, and they gave us a go. So this means that there's within 10 years or so, we really think that we will be able to launch this, and of course we have to be lucky enough. But there are many theories which predict that the amplitude of those fluctuations from early universe is large enough to be detected by this light bulb. So we hope that we will be able to see that within a 10 years of time, 10, 15 years time, I guess. Yes.
Okay, thank you very much, Dr. Sasaki. Now I would just, before we wrap up, maybe just ask you if you could, so are there, you as part and as chair of the division on
this is astrophysics.
I don't exactly.
Yeah. Sorry, I cannot hear you very well. So, what kind of what information you want to share?
Yeah, I was just going to ask you, are there any opportunities or any involvement of students in your division on cosmology and gravitation?
Oh, yes.
Or
yeah.
Okay.
Yeah. Actually, yes. And we will actually organize. Because of this pandemic situation, actually, it's very difficult to, have a sort of face-to-face meetings. And then so we decided to organize a virtual meeting. And now, in some sense, this is good for students from all over the world, because apart from time difference problem, that you can actually join from anywhere. And in this coming November, we are having this DHCG workshop on astrophysics and cosmology and so on and so forth. And this will be organized by one organization in Korea called APCTP, Asia Pacific Center for Theoretical Physics. And I think they have already put a website for that workshop. So if you remember this name, APCTP, yes, and look for some website, and then I'm sure you can find it, and the students can find it. And if a student wants to, at least maybe listen to the talks, or maybe to make some presentations, they have a chance. Yes.
Okay, thank you very much, Dr. Sasaki. Now, before we finish, I would just like to ask you if you have any final statement or any final message for students that watch this.
Well, yeah, well, I just do hope that this was interesting enough and make them interested in this area of research. And I'm very happy to answer any questions. If you have any questions, just contact me. I guess you can find my email address anywhere. And I hope you have a nice future, bright future, and be healthy away from this pandemic. Okay, yes, that's it.
Okay, thank you very much, Dr. Sasaki. I want to thank you again for accepting the invitation for this very interesting talk. And also thank everybody that's been watching us and everyone that watches later. IAPS at a Distance will continue with more sessions already tomorrow, next week. So thank you, everybody. And thank you again, Dr. Sasaki. Have a very nice day.
Thank you. Bye-bye.